Okay. So, yeah, just in case you need to revise something, you can go back and watch the recording. So, let's create a new project. Week 4. Do you know how weeks do you have in the term? 14. So now we're in week 4. Um, okay, week 4. Section 5. Python file, spiral. So import turtle as usual. Not as usual, st. But okay. Define function spiral. And we will have two parameters, the number of the segments in this spiral and the length of the first segment. And we will start with something that we didn't talk about last week. We will write the recursion without explicitly writing the base case. Because what we did last time, we did if n equals 0, the pass, else total forward by 90, total, oh, sorry, forward by length. Then, for example, left by 90. And then we call our function again with parameters n minus 1 and length, let's say, minus 5 units, because if I do minus 1, it will be very close. Each line will be very close to each other. So let's just run, and then I will tell you how to read of the first base case. Let's do 20 and 200 size. Okay, it works. So we could do, instead of if n equals 0 pass, else, we could do just if n is greater than 0. So let's think about why it works without base case. I mean, there should be a base case, but it's kind of implicit. So let's think about when n equals 1, and we call our function with parameter 0. What happens at this point? So we call our function with n equals 0, but if statement isn't satisfied. So what will return or how it will be executed? So what if I try to just to type instead of uh, print spiral with parameter n 0? What I will get? Any function that doesn't have return statement returns none, and it returns none. So the same happens is when we call our function from itself with parameter 0, it still will return none. And it's the other thing that also is interesting. If we do the base case, if n equals 0, and instead of pass we type return without anything after return, it also will work. And again, if we print, because I print and now I have n0, so it goes in if statement and it prints none. So even though we didn't type anything what this function should return, it still returns and it returns none. So just saying that sometimes you can write your code without base case, but this base case still will be in your function. So let's modify now our function such that it returns the length of the curve. And it's actually similar to your homework lab. Evaluate the zigzags length recursively. I mean, of course, if you have your shape and then twice smaller shape, then the sum of lengths of these twice smaller figures is equal to the length of the bigger figure. And some students have, can I just return depth times the length? Because the depth, because it's always doubles, the length of your figure is the same as the length of one figure times the depth. And the answer is no, you should use recursion, the function with return statement. So to evaluate the length, we will return 0 for the level 0. And when we call our function, we will store this value as the length. So like can we call that partial length, and then we will return this partial length and the length of the current segment. So let's do maybe two levels. So it looks correct because my first length was 200 and the second one 95. So this is how you can do calculations in your lab tool with recursion. And now let's think about I mentioned in the beginning that the first function was tail recursive, and the second function, which calculates length, is not tail recursive. Let's think about why it's the case. So when we just drew the spiral, um, I believe it will work. Yep. So the last comment in our function was the call of this function. So if you remember factorial, uh, factorial. In factorial, the last call was not the call of the function, but it was the call of the function times the parameter on the current level. So this is the difference. And if we look at the function that draws a spiral, it has as the last call, the call of draw spiral. But if we look at the code for the length, we see that first we should calculate length, but then we should add this length to the current length. So it means that we should do the backward path when we calculate the length of 0, then we calculate length of 1 plus 0, then of 2 plus the previous length, of 3 plus the previous length, and so on. In case of drawing, we just reach the level 0, and then you will still see the stacks, the backward stacks in Python, but the variables in those stacks, they won't change. They won't be changing. So this is the difference. Okay, maybe it's not clear for now. Let's take a look at the factorial example. And then we will go back to back to the spiral. Factorial. So our like last week's solution was factorial of n. When we have return statement, we should do the base case. We should type return if we want to get the number to be returned. Otherwise, we will get none. And when we will sum up, none plus a digit will give you an error. So if n equals 0, return 1, else return n times factorial of n minus 1. And if you remember, let's print it. Factorial of 3, for example. It's 6, so it works. And if you look at the execution stack, so you have the function with n free. It checks the condition. The condition was false, so it goes to else statement. In else statement, it sees that free should be multiplied by factorial of 2. So it creates a new instance of your function, and with n equals 2. And again, it checks the condition. Condition is false, so it goes to the next with n function with n1. Then it calculates 1 times factorial of 0. Finally, when we reach the if statement with 0, n equals 0, then we return 1. But after that, we go back to return, and the instance of function with n equals 1 will be multiplied by 1. Next, we don't move from this line, so we don't go to check the if statement anymore. We just multiply the n from the current level by the result of return of our previous function. That's it. But we had this backward path. So how to read off this backward path? So let's think about how to modify this function such that the final call is just the function itself without multiplication. And for now, you are allowed to use global variables, even though we don't allow to use this. But maybe if you think about how to make this function like without backward calls with global variables, it's fine. So what you can think, what if we just create a variable, global variable, and we'll multiply this global variable by n. And in the end, we will return the result. So what if we just create a global variable we initialize it by 1 because we will multiply by n. And it's very important to return this accumulator on the level 0. And here we will just, we should also say that it's a global. And here we just will modify our global variable as multiplying by n. Yep.
Why do that? Like, when would this be used?
Yeah, but I will read of the multiplication by n here. So it means that now the last line of my function, of the code of my function, is the call of this function itself without any additional variables from this level. So it means that when we reach the level 0, it will always just return it's actually the question, what it will return. So first, let's see if it works. I hope you know that these syntaxes we are using instead of writing n times accumulator. So it's called prefix operation. So instead writing accumulator equals to n times accumulator, you can use this prefix notation. It means that this variable will be multiplied by n. So let's see if it works. Maybe I'm lying. So, well, the value is 6, so it looks like it's working. Um, so what is going on here? We created a global variable, and then we just multiply this variable by n. Then we call our function with n minus 1, so this variable will be multiplied by n minus 1, and so on until we reach n equals 0. But it's really interesting what happens is that n equals 0. Maybe I can do debugging. So first we enter our function with n equals 3. Then if statement is false, so we go to else statement and we change accumulator, the global variable. Then we go to return, and return we call our function again. So it creates a new stack here. So again, we multiply accumulator, but now it's multiplied by 2. Then it creates a new, and for now, the accumulator value is 6. So now n is 1, accumulator value is 6 because it's 6 times 1. And finally, the last step, we reached n equals 0. So we go to if statement. In if statement, we return actually the value of factorial of this accumulator. But if we look at our function, so there is n, there it calls another function, but then there is also return statement. Return statement. Then it calls this function with n minus 1, but this function also has return statement. And so on up to level 0. Oh, it's hard to see here. In level 0, it also has a return statement. And it returns the actual value of factorial. But then it goes back, and the final return statement, what we will actually get in our print statement, this return will be delivered here.
Are they faster, the tail recursions?
The tail recursions are faster.
Okay.
Yeah, so now we will see why it's the case. So, well, the first explanation is that it doesn't use the backward path, but it's not 100% true, because in other languages, programming languages, the there is optimization. And if your code has tail recursion, it doesn't do the backward path. In Python, you still will see the stacks, but the main difference is that in those stacks, nothing happens when it goes back. So for now, my point is that when we call our function, the result of this function uh, is given by a return statement on the first level when we just entered into this function. Does it make sense? Because we entered the function, the condition was false, so we go to return statement. Then in this return statement, we go to the next level, like deeper, 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 but still this is the last code that will be executed in this function. So let's think what we will have in this return. If in this return, we will see return from the previous level. Does does it make sense? In this return, we will see the return from previous level, and so on, up to the level 0, where the return actually was the desired value of factorial. So I hope maybe you can see now how it works. We calculate accumulator. Accumulator has the desired value at level 0, and then we just return this value on all the previous levels without any changes. Okay, maybe. Maybe it's, let's see. So now on level 0, it returns accumulator. And now I believe it will skip the line accumulator and it will go directly to line return. Because now we're going like in backward direction. And you can see it always stays in this line. Okay, I hope I kind of explained the difference between general recursion and tail recursion. So let's now read off the global variable. The modification is very simple, but you need to know about default parameters. So default parameters um, right. So let's create a function, my function of two variables, A and B, but I will use the syntaxes that we didn't use before. I will assign B value 10, and this is called the default parameter. So how it works, I will just print the values, format line, A equals A, and B equals B. Oh, I want to see the function. Okay, let's do it again. Function. And now I will call this function my function. And here I will change the order of the parameters. B, for example, equals 0 and A equals 1. So the first observation is that if when we call function and we use the names of the variables explicitly, we can change the order of these variables, but still they will be assigned correctly. This is the first observation. The second observation is that, yeah, if I just write 0, 1, now I will have the first variable as 0 and the second as 1. The second observation is, what do you think if the function takes two arguments, but I will call this function as the function of one argument. Or so what do you think will happen? Will I get error, or maybe I will get some values assigned to A and B in my function? I will just print. So you can see that the first parameter was assigned as 0, but the second takes the default value. So this is what is called default parameters. So instead of using the global variable, we can use the default parameter. So let's modify our function. So forget about global variables. So yeah, we don't allow to use them, but we will create here additional parameter accumulator, and we'll assign the default value 1. So instead of return accumulator, I will return this accumulator, the local variable. So how should I change this recursive case now? So instead of accumulator, I will use this local variable acc, and in this factorial, I will call this factorial with this. Actually, it's easier just to type here n times accumulator. I mean, it's the same. And now I can call my function of two variables, but still as a function just of one variable. And it returns 6. But what happened here? The last line of our function is just the call of the function itself. So we don't multiply anymore this result by n from this level. So can you see that this is that when it reaches the level 0, it will return the desired factorial value, and then it will just, on the way back, it will just return this value. So kind of the backward path is trivial. Okay. What's next? Okay, let's take a look at the substitution trace. Yep. Do you mean factorial with accumulator? So let's see. Do you have the same syntaxes? So factorial of n and accumulator equals 1. Then first if statement, return accumulator, else return the function decrease n and n times accumulator. So okay, works. Yeah, so it's kind of okay, you will see now in the substitution trace how it works. So this is the last week substitution trace, the general recursion. This is the recursion with accumulator or tail recursion. So we enter in our function with parameter for n and value for accumulator. Then we multiply this accumulator by n. So now accumulator is 5. And we call our function with these new parameters. N by 1 is smaller and accumulator 5. Then we multiply accumulator by n, so by 4. And then we call our function again with n by 1 smaller and with new accumulator. Then we multiply accumulator by n, in this case by 3. And we call our function with smaller n. So then in this call, we update accumulator. We multiply this accumulator by 2. And then we call our function like with smaller n. And when we reach n equals 1, accumulator actually has the desired value of factorial. And then we return this value on the base case when n is 0, we have return accumulator. And then on all other levels, we just return this value. Does it make sense? I think, oh, this is the example of the spiral with accumulator. So we create additional accumulator for our spiral function, initialized by 0, and then we update this accumulator, just add the current length, and then call the spiral with smaller number of the level and with new value of accumulator. I think we can stop here and do a break. And after break, we will talk about wrapper functions and decorators. So I think it will be more interesting. Well, let's do 10 minutes break. How much time is it? Yeah, we can start at 6.
See that.
I wouldn't say no.
What's that?
With Jim, this is happy.
Yeah, I'm gonna go.
To take photography and then go into post-photography. That was you know, automotive multiple research goes into like the cryptography and how even if like you quantum computers don't work, you know, with Rosberg, like big cryptography standards are still there. I had to know from the try to reach out to. Switch code feature.
Oh, you guys are about these. I think it will write a nice plan.
This is, you know, finish a book in a week. Finish a book in a lecture series in a week. So,
But this is for self-study. Oh,
yeah,
maybe you
great
could
path.
just do the
No, they read. Why? Did you see the wall? Which one is that? No, I don't know. I was very much. You listen.
okay.
Yeah, I'll show them. Oh.
What mathematics source? But it recommends all the what's called like online courses.
I know. Oh, did they grow apart? I can't believe that. You have.
Or maybe it's like the general, so quantum computing basis, programming, advanced specialized topics. So cryptography is just one of the specialized topics, actually.
It's inverted. It's that stuff. What stuff is good? You left it on the table in the shed, dude. I don't know if you wanted that. It's not.
Oh, maybe, yeah.
That's the college classes. I'm pretty shy. I know your economy is very used to stealing things. It's a good.
What have we done so far? What have we done so far? Recursion. There's a more review of recursion. Pretty much exactly the same thing. Well, it seems to vary along that. Is that what you're on?
Well, I'm sure that'll be very easy for grad school to get.
You read journal. I'll be the wall.
Yeah.
Like
Easiest.
not many universities have the specialized program for this.
For my junior,
Uh,
all the other classes were.
I don't know. I don't know if they actually. I don't think a lot of these actually have programs themselves in it.
Well, it says program.
Oh, let me copy.
Oh, it says quantum science and engineering, even PhD and master degree.
There's undergrad courses. I don't think those are programs in themselves. Yeah. Yeah, these are courses. These are all courses.
Yeah.
Oh, you Chicago. Yeah, depression.
Oh yeah, you can do some search with ChatGPT. I believe, and maybe you will find some information also on the site of these universities.
Yeah, I'm gonna check that out.
Yes.
Probably already. Not three of them? Uh-huh. No, you got three right here. You're not gonna give me any? Yeah. No. I'll give you some gold answers and what was happening. I know this is true. How many grams sugar is that? I don't care. I don't wanna know. Can I see? I'll tell you. Yeah, let's go to. How much in the right? They read it. No, it's not. Come on.
Yeah.
Bro, that's like a quarter pounder with a. Like my weight.
Oh, that one. Oh, yeah, one of those.
Oh, well.
Oh.
Really? Bro, you go back. Oh. You look at it. The reading. How many are you? Are you?
The lab is just
Yeah.
I like stuff. No, not here. So like, you know, yeah, I can get fun of it, right?
I saw someone get that.
Well, you don't really have a president. Yeah, I got the. No, you can't. It makes sense. It makes sense. You gotta give it. Give it. It's not good at making up information, it's really good at summarizing.
Sorry, hi, everybody. I'm gonna read the first to the last line of our introduction are
Just try to do that.
Like a shoe.
No.
I don't think
You do now.
that's simply my low mix to Monday come to gym. Many times.
Every weekend.
You
don't have to. I know.
Okay, so let's continue. And now
On the way.
imagine that I didn't tell you about the default parameters. So let's say you don't know that you can assign the values inside the function. And how can we work with how can we convert a function of two variables into a function of one variable without using default parameters? And the answer is we create a helper function or wrapper function. So in this example, we create a function factorial of one variable, n, but it calls the function of two variables and assign like manually the value for accumulator one. Does it make sense?
That works.
Yeah. So this is what is called wrapper functions, when we use one function to call another function. Let's talk about the special case of wrapper functions, decorators. So let's create a wrapper function here. So let's say I don't want to use the default parameter, and I will just create a new function wrapper function for factorial of one variable, which will just return the factorial function of two variables and an accumulator. And I will print this wrapper function. First double check that it works. Yes, it works. It returns 6. Another way to do is to create a decorator. So let's create the decorator function for factorial, for example. The difference between wrapper and decorator is that wrapper returns value, decorator and input and output is the function. So I will use for decorator as input just a function name, identifier. So that's why I'm not using the parentheses, because it's just the name of the function in our machine memory. And inside the decorator, we create another function. Typically, we call this function inner, but you can use arbitrary name for the local function inner. And the parameters of this function are the same as parameters of the input function. So we will call our function with parameter n, and this n will be also used as the parameter of this function inner. In this inner function, we can return, for example, the factorial with two variables. And the return of the decorator function will be this function inner. Again, without parentheses, because we return the function, not the value. And now let's... So to call this decorator, the syntax is in Python, we should use add symbol, decorator. And here we define a new function, some function, my function, with which reads only one argument. And because when this function will be passed to decorator, decorator has return inner function, and inner function has return statement. I can skip the return statement in my function. And let's see if it works. So I will call my function, which technically doesn't return anything. My function just do nothing. But it returns the factorial of 3. So again, this function the decorator works exactly the same as a wrapper function. So it takes your function and parameters inside this wrapper function. And here it's actually does something with the parameters which your function reads. So if we look at these two examples, a wrapper function is just 2 lines. Decorator function is also 2 lines, but we also had to write this decorator function. So, for example, when we can use decorators, because it's obvious that wrapper functions factorial. They look much easier. Just call another function inside. So let's think about when we want to use wrapper functions and when we want to use decorators. So for example, if we want to print the execution time of our function, we can write a wrapper function. And in wrapper function, we can do, you remember, start time, then call our function, then end time, and then we can print the difference between the start time and stop time. And we can do the same in a decorator. So what would you prefer? For example, if you want to use this execution time for every function that you create. So what would you prefer? To write every time a wrapper function, or just to write one decorator and before every new function add one line? Yes. So of course for factorial, we're not so mentally sick to create several functions which evaluate factorials. It's enough to have just one function, and then it's easier to write a wrapper function for that. But if you want, for example, have the execution time to evaluate the time of execution of our function, and we want to have this for every function, then it's easier to write the decorator. And here is the example how the code looks like. We initialize the variable start time, then we run our function, then we create a variable stop time, and then we print the execution time and return the value of our function. So this is the decorator for example, the time checking. Okay, so we won't use decorators except one case in this class, but it's good to know about decorators. Now, we go from recursion to loops. Here's the code for tail recursion to calculate the length of the spiral. And here you can kind of visually observe that this code was just transferred under while loop. There is one change. We changed the number of segments, not inside the function, but explicitly here. But the rest of the code is the same. So first, what is that while loop? For example, I will create a variable let's say 3. And I will do a while and statement iter is greater than 0. And here I will just print this variable. But if I don't decrease this variable, the statement in while loop will be always true, and we will get so-called infinite loop. So to avoid this, I will also decrease this parameter with each iteration by 1. Oh, print infinite. Okay. Print iter, not inter. Okay. And here how it works. We enter with parameter with variable iter equals 3. We print this value and then we decrease. So now our variable ether has value 2, we go back to the while loop. It's still greater than 0. We print, decrease by 1, we have 1. We go back to the loop, we have value 1 is greater than 0. We print. Now the value is 0. And when we go back in our while statement, now it's false. So we go out of this statement to the next line. So this is how the while loop works. Now let's take a look at the code for the spiral length. It looks a little bit weird. While statement is always true. So the statement is never changing. So it's kind of the infinite loop. But here we have the check for the number of segments in our curve and a return statement. So if interpreter sees the return statement inside a function, inside a block of code, it will do the return, but after that, it will go outside of this block of code. So that's why we won't get the infinite loop. When we reach the number of segments 0, we have return statement. And the return statement will bring us outside of this function. It's not true for recursion, because in recursion, return returns the nested function. So that's why we still call our function again and again. But if we don't call our function itself, after return statement, we leave our function. Okay, so I hope it's clear what is going on here. So we have the number of segments. We move forward, rotate 90 degrees. We increase the total length parameter and decrease the length of segment and number of segments. And when we reach the number of segments 0, we return the total length and leave our function. So let's write the same for factorial. Oh, wait a second. The first thing is to rid of this weird while true. So we have this while true, but we can do something more elegant and check this statement if the number of segments is greater than 0. And if it's 0, then we'll just go out of the while loop. Okay, now let's do the same for factorial. The first factorial is the last week factorial, the general recursion. The second factorial is the factorial with accumulator. So it's a tail recursive factorial. And finally, we transform this into while loop. So we initialize accumulator by 1, and then do while loop. While n is greater than 0, we multiply accumulator with n and reduce and decrease n by 1, and then return the accumulator. So with loops, we have so with recursion we had substitution trace notion. With loops we have timeline notion. So timeline is just a table where we have the number of iteration 0, iteration 1, and so on. And we just list the values of variables at each iteration. So for example, for factorial for this function, in the beginning, accumulator is 1 and n is 4 when we call factorial of 4. On the next iteration, accumulator was multiplied by n. So n was 4, n times 1 is 4. And new value of accumulator is 4. But n was reduced by 1, so n is 3. On the next step, accumulator was multiplied by the current value of n, so 4 by 3. This is the new value of accumulator, but the n was decreased by 1, so the new value of n is 2. And we can continue. So on the next step, accumulator will be multiplied by n. We will have 24, and n will be 1. And we will stop here because 24 by 1 is 24, and here we will get 0. So this is called timeline. So in 2 weeks, we have a midterm, the first midterm, and there you will have some problems. Convert general recursion into tail recursion, or convert general recursion into while loop. So first you convert into tail recursion and then into while loop. Or fill in the timeline for loop, or trace the or to write the substitution trace. Okay, so now the last problem for today. You remember last time we created Fibonacci function, and it didn't work for n equals 80, for example, because it had a lot of recursive calls. So let's convert the Fibonacci function to tail recursion, then to while loop, and then write the substitution, the timeline for new Fibonacci. And you will see that this Fibonacci converted to tail recursion or while loop will work even for very large numbers. For thousands, it will work very nicely. Okay, so let's do it together, and then we'll have a quiz. Okay, new file Fibonacci. So you remember in Fibonacci we had 2 base cases. So let's write first the old Fibonacci function. If n was 0, we return 0. If n was 1, we return 1. And otherwise, we return the sum of Fibonacci of n minus 1 and Fibonacci of n minus 2. Fibonacci of n minus 1 plus Fibonacci of n minus 2. And this was the main problem, because here we had this increasing time complexity. Because here we had to go inside function fib n minus 1 and inside function fib n minus 2. So we had this binary tree growing from here. So how to convert this function to the function with accumulators. So let's add just two accumulators because we have two base cases, accumulator 1 and accumulator 2. Accumulator 1 will correspond to previous Fibonacci number. Accumulator 2 will correspond to the Fibonacci number with index n minus 2. So if n is 0, we will return accumulator 1. Well, oh, wait a second. We will return accumulator 2 because or accumulator 1, let's see. Maybe we should flip this accumulator 1 and accumulator 2. And in else statement, we will call Fibonacci of n minus 1 but accumulator like the Fibonacci number with previous index n is the same as accumulator 1. Accumulator, wait a second, is the same as accumulator 1. So now it will be the same as accumulator 2 because accumulator 2 corresponds to the Fibonacci number with index n minus 2. And Fibonacci number with index n minus 1, it's the Fibonacci number with index like previous one. So it will be accumulator 1 plus accumulator 2. Because accumulator 2 corresponds to Fibonacci with n minus 2, and accumulator 1 corresponds to Fibonacci with n minus 1. So that means that here we get the new Fibonacci number. But to the Fibonacci number with n minus 2 index, we assign the Fibonacci number with n minus 1. To the position x2, we assign x1. And I think it will work. So just we need just what we will return accumulator 1. I believe it's correct. Let's try to run this function and see if it works. Print Fibonacci of 5 should be 5. Fibonacci of 6 should be 8. Ah, yeah, we can initialize like the nearest number is 1, the previous one is 0.
Accumulators for n minus 1 and n minus 2. Right, initially the first two accumulators n minus 1 and n minus 2.
Yeah, let's first run and see if it works, and then I will answer the question. So, okay, the number is 3, but Fibonacci is 5 should be, so I should return maybe here 2 and here 1. Let's see. Okay, now it works. And Fibonacci of 8, oh, sorry, of 6 should be 8. Yeah, it works. Okay, so now let's look at the code. So actually we will convert this code into while loop and write this timeline. So we will see how these variables are changing, but let's take a look here. I will answer your question. Accumulator is the sum of Fibonacci numbers. And it begins from this Fibonacci numbers with index 1 and Fibonacci number with index 2. So we kind of go from the opposite direction. N is, for example, 5, but this accumulator is 0 plus 1.
Oh, I see. So
Then N is 4, and accumulator is this number plus 1, so it will be 2, and so on. So we kind of go from like opposite directions. N is decreasing, accumulator is accumulating.
Right.
So now let's convert this into a while loop, and we have the instruction. We should just write while true and copy paste the code. So let's convert this into while loop, while true. So we don't need any more accumulators here. We just create local variables, ec1 and ec2. While true, and we return accumulator 1. So that's fine, but we need to accumulate accumulators. So here we should write, it's another interesting syntaxes of Python. Accumulator 1, accumulator 2 equals to accumulator 1 plus accumulator 2, and accumulator 2 will be assigned accumulator 1. So in this line, under the hood, it creates like additional variables where it stores the sum of ec1, ec2, and ec1, and then it assigns these additional variables to new values of ec1 and ec2. But we can use this syntax. Let's see if it works. Oh, it returns 1. Oh, okay, because let's see what's why it returns 1. Oh, I believe because I need the return statement only if n equals 0. So I don't need everything here. Okay, now it's infinite loop because I didn't decrease the n. Sorry, I should also decrease n by 1. Okay, and now it works. So this is the Fibonacci with while loop, and actually now we can calculate Fibonacci of 80, and it will work. Well, it's a big number, but it's, yep. Yes, sure. So this is the Fibonacci with while loop.
You know how we go.
And the last, so let's see if there are any questions about this function. So maybe we can do it better and write while n greater than 0 instead of while true. But while n is greater than 0, decrease n, reassign the variables, and return the value. So yeah, it works. So it looks better. The last task for today to write the timeline for this Fibonacci. I will do this maybe on the right here. So the timeline is the table, the number of iteration, and all the values of the variables. Like here we have the variable n, we have the variable accuracy, accumulator 1, and accumulator 2. So when we enter our function iteration, we typically begin counting from 0 because in Python the indexing goes from 0. So iteration 0, but in other words, iteration 1. What is the value of n? Oh, it's 80. Let's do 5 or let's do 5, for example. So the value of n will be 5. The sorry. The accumulator 1 has value 1. Accumulator 2 has value 0. Next iteration. Now, could you tell me the values for new iteration? What is the value of n? 4, because we subtract 1. What is the value for accumulator 1 on the next step? 1. We should sum up the accumulators on the previous step. What will be the value of accumulator 2? Also 1, because it's the same as accumulator 1. Next iteration, the n is 3. What about new accumulator 1? 2. And accumulator 2 is still 1 because accumulator 1 was 1. Next iteration, n is now 2. Accumulator 1 is the sum of accumulators, 3. And accumulator 2 is 2. And maybe you can see in the last line the Fibonacci sequence. 0, 1, 1, 2. Next should be 3, then 5, then 8. So let's do just one more, and I think you have the idea. Oh, sorry, what is going on? Iteration 3, iteration 4. N is 1. accumulator 1 is 5. Accumulator 2 will be 3. And the last iteration, okay, it will be the last one because now n will be 0, and this case won't be satisfied. So, okay, we're almost done. So when we have iteration 5, we don't enter this while loop. We just go to the return statement and we return the value 3. Wait a second. But the value should be 1. Wait a second. Oh, maybe I should return accuracy 1 instead of accuracy 2. Let's double check on this smaller number.
Accumulator 1 is what you want, right?
Oh, let's see. Fibonacci of 5 is 5. It works correctly. Yeah, but I return accumulator 2.
Wait.
Oh, maybe I did as let's see, accumulator 2. What a bummer. Like everything went smoothly and the last return function um, doesn't seem. Oh.
And then.
I, I, I don't know what is the problem. So the Fibonacci of 5 is 5. Uh, Accumulation.
If you put accumulator 1, there's a double word.
It returned me 3, I believe, if I put accumulator 1.
They gave me. They give the next number.
Oh, it gives, for some reason, it gives the next number. Um, oh, I believe that my timeline should be shifted by 1 because when I enter with iteration 0, I change n by 1 in this iteration. So it looks like okay, so something is weird with timeline.
Can you change where the return is?
What?
Can you change where the return is? Like make it.
We can just print like here. So when we enter while loop, we have this 1, 1, 1, 2, 1, 3, 2, 5, 3. So, oh, I see what's the problem. So when we enter our loop, the accumulator 1 is 1 and accumulator 2 is 0. Then n is still 5. So the value n should be shifted here by 1. So then the value n, when we enter, the value n is still 5. And that's why we have just one extra column here. So here we'll have 8 and 5. But yeah, I think it's because we
But if you put, if it returns like accumulator 1, then it should return 8, right? Also, you can confused by that.
yes. Okay. To be honest, I switched the order of accumulator 1 and accumulator 2, and maybe that was the issue. So, for example, in my code example, accumulator 1 corresponds to Fibonacci number with n minus 2.
If you make
So maybe because I switched them around, we have this problem.
in the while loop, if you make accumulator 1 equal to 0 and accumulator 2 equal to 1, then it works.
Oh,
You return.
you're saying that I should switch the accumulators. Oh, it works, guys. Okay, so my bad. You can see now that now we have our timetable. So it means that I calculated wrong the timetable.
Yeah, we have.
But now if we change, oops. So Jesus. Oh, sorry, it's week 4. Here is the password. Maybe.